Sampling error is such a fundamental concept of statistics that so many psychologists, and not psychology students, psychologists, right, like with PhDs and researchers, don't understand what it is and how it works. So if you'll bear with me, I want to take just a minute and go through some R code to show you a little simulation that, again, many of you have already seen. Every statistic is subject to sampling error, and it's a property that comes from the fact that your sample doesn't perfectly match the population. Everybody knows this in practice, everybody understands it conceptually, but not many people actually see it. And so I want to show you what it actually looks like in practice and make a case for why we even have null hypothesis significance testing at all, right? Which I think also a lot of people don't understand and don't get. Smart people that write papers on the topic. So, so what I'm going to do is I'm going to simulate data of a correlation between two variables. And so what I'm doing is I'm simulating 1,000 replications of a study. So anytime you've got like a nested thing like this, you work from the inside out. If this doesn't make a ton of sense, don't sweat it too much. It's not important that you know how to do this in R. What's important is that you understand what I'm doing, not necessarily how I'm doing it. But what I'm doing is I'm simulating a random variable with 50 cases. And the mean of the random variable is going to be 0, standard deviation is going to be 1. It's essentially just a z-score, right? But I'm simulating a random variable, and I could have made this metric anything. It could be 50, standard deviation of 10, doesn't matter at all, right? But I'm simulating a random variable with an n of 50, and I'm simulating another random variable with an n of 50. These two variables are uncorrelated. Like by definition, in the population, there's no correlation between these two variables, right? They are random. That means there is not a correlation between them by definition, right? And then I'm just calculating the correlation between them. And what you see is even though in the population there is no correlation, they're actually correlated at -0.21 in this sample, right? That is sampling error. The fact that I got a number that wasn't exactly the population value of 0, I essentially saw this by chance alone, right? Because I simulated these variables to be uncorrelated, but they were correlated in the sample. Why did that happen? I mean, it's sort of a circular definition, but it's because of sampling error, right? Like the fact that I only pulled 50 people out of this population, those 50 people I pulled happened to show a correlation between these two variables. Stuff happens, right? Like you can't control everything. And this is inherent in every sample you collect. No matter what research you're doing, no matter what your sample is, no matter how much money you spend on it, there's always some aspect of sampling error in it, okay? So what happens if I do this again? Let me just get rid of everything here and do it again. So this time the correlation was 0.11, right? In that random pull, if I do it again, what do I get? -0.20. Do it again. -0.31, so pretty big correlation, right, for two variables that we know are uncorrelated. So let's, instead of just me doing this over and over, let's do this 1,000 times automatically. And the way I'm going to do that is going to wrap it in a for loop. Do this for I equals 1 to 1,000. So do this 1,000 times. And what I'm going to do is I'm going to build a little container called core data.n equal n50. And I'm going to set it to be empty. And every time I calculate this correlation, I'm going to put it at the end of this, in the last, like at the end of this list of stuff. So after I run this, what I've got is you can see 1,000 correlations printed out here. And you can see that they're all now in this kit I made, or this train I made with 1,000 boxcars on it with those 1,000 correlations. All right, everybody see that? So what I've done is 1,000 times in a row, I've done just what I did manually. I made two variables that I know in the population are not correlated. I computed the correlation between them, and I wrote it down and put it in this little list, right, of 1,000 things. Okay, if I print this out, you'll see them. There's all 1,000 correlations I computed. Okay, and here's the important part. I'm going to hit the describe command. So what I see is that the mean across these 1,000 replications is 0, which is the right value, right? That's what I should get, okay? But in any one sample, it ranges anywhere from -0.55 to 0.44, and the standard deviation is 0.14. Anybody know what this is? Anybody that took my other two classes where we did probably the same thing, know what we're looking at here?
With the
Like, what
sampling
is this?
distribution?
Yeah, exactly. This is a sampling distribution, right? It's a sampling distribution of correlations under the null hypothesis. The null hypothesis is that two variables are not correlated, and that's what we've got here. We've got two variables that are not correlated, but we see an awful lot of correlations in here, right? The mean turns out to be the right value, and that's because the correlation is an unbiased statistic. In the long run, if you did 1,000,000 replications, you'll get, on average, the right number. But in any one sample, you could be pretty badly off. So imagine you're a researcher and you find a correlation of 0.55 between these two variables. Man, break out the party hat, right? Because you've got a big correlation there. That is something worth writing about. That's going to get published. Happy day. But you can see it's just flat wrong, right? Like that's not right. We know the right answer and it's 0. You got 0.55. So you were bad off just by the random Joe Schmoes that happened to sign up for your study. And there's nothing that can be done about that, right? Like nothing you can do to prevent that. The only thing you can do is replicate your study and have other people replicate it. This is in part kind of what's behind the replicability crisis. I don't want to get too far in the weeds on that, but I'm sure you're familiar with that. But essentially the replicability crisis is the fact that you've got all these published studies that people can't replicate. Well, why might that be? Well, what you can see is somebody might have done a study and gotten this crazy high correlation by chance alone, sampling error. And then everybody else that tries to do this study says, I don't know what the deal is, man, but I'm getting 0 here. The people that try to replicate get 0, they can't get their stuff published, right? Like nobody's publishing, hey, I replicated this famous study and I got a 0 correlation. People are like, well, you probably did it wrong, or it's not notable, or nobody wants to read about that, right? So that stuff never gets published. What gets published is the one that found this crazy high correlation. So, so this is sampling error, right? And I don't have it plotted here, but if I plotted it out, it would be a normal distribution with the mean at 0 and the thing. I'm going to plot it down here later on, actually, right? So let's take a look then. That's a great segue. What I want to do now is I want to run the same exact thing, but instead of N50, I'm going to make N500. So let's take a look at what happens there. Everything else is the same. Just printing out those 1,000 correlations. Right? These are the 1,000 correlations here. And then the key is I'm going to actually do the describe function again. So what happened now? Well, the mean's still 0, which is good. You would hope it would be, right? The standard deviation has come way down, and the min and the max have come much closer to the true values, right? And Dom, just like you were saying, like what this is showing you is you're much more likely to be right with a big sample than a small sample, right? You're not going to see a big giant 0.55 with a 500 person sample like you do in a 50 person sample. Okay, so how does this relate to significance testing? Well, what do you do in significance testing? Well, we have a p-value we compare things to, right? And if I go here to my 50, and I take those 1,000 correlations I computed with an N of 50, and I sort them, right? You can see they go now from lowest to highest. I can actually pull out the position associated with the 95th percentile, and it's number 950 out of 1,000. And then what I can do is I can pull that actual value, okay? And it's 0.233. This is for a one-tailed test. So what I'm saying here is if I have an N of 50, anything bigger than 0.23, I can be pretty sure I'm going to see by chance alone. I'm only going to see that number 5% of the time or less by chance alone. And anything smaller than that, I'm going to say, you know what, it's probably just a fluke, right? And that's exactly what significance testing does, right? That's literally why we do it. And I think this point gets lost on a lot of people. You'll hear people argue like, well, p-values are arbitrary, or p of 0.06 is just as good as 0.05. And I think it misses the point a little bit. Yeah, those things are technically correct, but the point is sampling error. That is the point of significance testing, right? Is you rule out sampling error as a reason for why you're finding what you find, right? Yeah, I do agree confidence intervals are important. Yeah, I agree that effect sizes are important, but ultimately, if you have a non-significant result, I would say don't even go look at your effect size. Don't even do it, because you can't be sure it's not a fluke. And this is what you're seeing here in the sampling distribution, right? So let me point out the let me make a histogram. I've got a histogram somewhere up here, I think. Yep. Let me show you the histogram for n equal 50. So basically what it's saying is that anything up to about 0.24, you're likely to see by chance alone. And again, the reason we know that is we simulated a bunch of data that we know are uncorrelated, and we still saw all these crazy correlations here, right? If I do this with the N of 500 and do the histogram down here, you can see it's a lot, right? Compare those two graphs, it's a lot skinnier, right? The sampling distribution, which is what this is of correlations, is way skinnier with a big sample. And that's why the p-value, right, for N of 500 is going to be a lot, the critical value is going to be a lot lower. Any correlation bigger than 0.072, we can be pretty sure is not a fluke with a sample of 500, whereas anything under like 0.23 or whatever, right, is what it was for N equal 50. So this is a long-winded way of showing you something that you already know, but maybe haven't kind of made quite as this explicit, that I think is critical to your understanding of basic stat, right? Like you really need to understand what we mean by sampling error. And I think so many researchers don't.